Okay, today we'll take on a new topic which is known as built-in test. So all this while we were what we had discussed is we started off with in this course how various faults can be diagnosed in a chip post fabrication. So what are the kind of test vectors we require to identify the faults which occur, and then how to post fabrication, how to put the test on an test bench, and you have an automatic test equipment and which would give the test vectors, and then you see the results and compare it with what is expected, and then you whether you pass the chip or the chip fails if it doesn't meet the specifications. Okay, that is all. That is what we did till now. Now what happened is the built-in test started with Gordon and Nedick. What they did is HP had a voltmeter. So they incorporated an self-test in this voltmeter, and that additional development time and cost by incorporating that self-test in the voltmeter was roughly 1%, but then the total savings was 5%, because post fabrication all those testing, they didn't have to do an elaborate test after manufacturing the test the voltmeter, right? So this is the history of a built-in test. Okay, so now it is extremely difficult, like if you have so many circuits and with a limited number of pins available. So with VLSI circuits, more and more complex circuits being incorporated in a small chip, but the total number of pins which is available is limited, right? So with millions of circuits within a chip, testing is become very difficult. So conventional testing means now post fabrication you need to give a test vector in one of the pins and take it and observe it from other pin and do the testing. So this is again, it is becoming dense and faster. Okay, so that becomes an and test pattern generation also, when you are doing a test from the pins. Okay, so that means the entire circuit gets energized. Okay, so the test pattern generation, you can't when you're, because you have controllability and observability of only a few pins at the output. So the entire chip needs to be powered, and then you need to test that. So it becomes even more difficult with because now it becomes like, it acts like a big system. Okay, so you have to test the system. So the test pattern is becomes very complex. Okay, test equipment, and again it is very costly. Test data needs to be stored, and these things becomes costly. So these are some of the limitations of the conventional testing. And then we can't do at speed testing, right? Because within the chip, suppose it has been designed to work at a specific speed, but while testing, obviously we take the outputs through the pins, and there will be bondings and things like that. So at speed testing may not be possible, whereas within the chip we might have, there might be a clock and intra chip wiring and all won't have that kind of inductance and capacitance. So we can design modules to work at a much higher speed, but testing from outside at that speed may not be possible. So that is another limitation, right? And the test designers may not be aware with small module design of the small modules. So that is another small issue, lack of skilled test engineers. So these are some of the issues in the built-in test. Okay, again for very complex VLSI circuit, again we can't do 100% stuck fault and coverage, because once it is each module might have some test vectors which could do 100% fault coverage, but when you speak from the chip point of view, once it is fabricated, then it works like a cascaded connection, right? It starts working like an full system, and in the full system we may not be able to do no, the fault coverage, although there might be a test vector no, available for a small module, but to get that test vector at that particular input of that module when it is cascaded and when it's working as a system may not be possible. Okay, so for all those things, built-in test is a solution for that, and we'll talk about how built-in test can be built-in system test. Okay, so self-test. Okay, so that is what BIST stands for. So we'll see that, and even the quality of test also. Okay, because all those interconnection errors and things and all, they all can be removed, and because the BIST blocks are within the test. Okay, so it is so though all those elements and probability of things going wrong while testing outside the chip, and even that is eliminated. So you could say that the quality will improve, and since each module will be can be tested independently of the other modules in an built-in test. Okay, the fault coverage also will be more. These are again some of those problems. It is difficult to carry tests simultaneously involving hundreds of chips, right? So you are fabricating so many tests. So each one of them needs to be put onto a test bench. Although some of the test equipments provide up to 16 chips at one time, you can put it on there and do the test. Okay, so you need to have so many test equipments, and if you are trying to fabricate say 100 chips a day, and each maximum a test bench would permit only 16, and the testing itself would take few hours, then you see there is a bottleneck there. Whereas BIST doesn't require an test equipment. Okay, so you could do some localized testing, and the entire testing process can be faster. In the earlier days, when the chips and all were fabricated on the PCBs, okay, then the bed of nails, what they call, on the PCB on the back side, you find all those soldering points, right? So it was possible that you could give some test signals on those soldering points, and power applied only to those components on the PCB on which the testing is done, and you could do the results. But now with the VLSI chips and with surface mounted technology and all, so we can't do that kind of test. Okay, earlier once if you have to check the system also, right? So when the system was being checked earlier days, you could put that onto a test bench where some probes could connect on to those soldering points and do the testing. So now with the SMT soldering, all those things are ruled out. We can't do that kind of testing. So you have a chip versus cost versus tester. Okay, so the tester cost and the overall testing cost will be much higher than now if you have as compared to if you have a built-in test within the chip. Okay, so that is why today, modern day, most of the chips they come with MIST. Almost 100% of the chips comes with BIST. Like when we power on our laptop or desktop, you see, or even for that matter mobile or any device with a VLSI chip, it runs an BIST program itself, and if there is a problem, it would pop out that okay, there is an issue with the system. Okay, and also this is known as a chipboard versus system downtime. Okay, now let's talk about say some module of an aircraft. Okay, it has got several PCBs involved. Now when you power on the system, it would run a BIST and say, okay, this particular board, okay, is there is a issue with this board, okay, right? or it can say there is a problem with this particular LRU. LRU stands for line replaceable unit. So the BIST runs on the system and tells, okay, this particular board has got some issue, it has failed the test. So you could replace that. Since it is line replaceable unit, in the field level you could just replace that board and put the system again in a working condition, make the system on a working condition. So the entire aircraft need not be grounded till that board is repaired. Okay, so that particular board can be sent for further analysis and repair. Correct. Same holds good with your, say, you are on a laptop or desktop. When the system runs, if it says, okay, there is a problem with the RAM or there is a problem with the hard disk, it would pop out a message. So that particular module can be plugged out and it can be sent for repair, but that doesn't make your system down for long hours till that board. So you can replace that particular board. Okay. So what a built-in test does, initially it will run a test and it will identify what is the fault with a sub-assembly. Okay, and then it will pop out a message that, okay, this particular sub-assembly, there is some fault and which you could replace, and you can continue. You don't have to put down the entire system. Okay, so that is a kind of early fault detection and giving a caution to the user. So it enables, it brings down the downtime of the entire system. Okay. Now, how an BIST work is, like there will be several sub circuit. If this is within a chip, okay, first it can be within a, this is a chip. Okay, on there could be several chips like this. So this is a snapshot of only one chip. Now within the chip also there could be several circuits. Okay, so it will take one particular circuit, and within the chip there will be a pattern generator which will generate some test signals. Okay, so and it will give to the circuit under test. CUT stands for circuit under test, and it will give to a response analyzer. And if it is okay, that particular circuit, then it will go to the next circuit. Okay, so there is a test controller. So first, part by part, all the sub circuits will be checked within the chip. Okay, and then the whole chip as a system will be checked. Okay, now once there could be multiple, so all the chips will undergo some test. So this test needs to be incorporated in the VLSI design in the chip, and then it comes to the board. Okay, so on the PCB board there could be several chips. Okay, so there could be some test controller on the board. Okay, this could be as a separate chip, or the controller itself can be a separate chip, or it could be in one of the chips itself. In the CPU itself there could be some test controller which will test the this part CPU's communication with the RAM and things, right. So that part also could be incorporated within the chip, or it could be outside external. So multiple chips on the board will be checked, and then you have there could be multiple PCBs on a particular system. So at the system level also there could be some test controller and some test signals. Okay, so this is the hierarchy. So here within the chip, if some circuit fails, okay, then there could be an option of some if there is an fault control fault tolerant design available, maybe that part of the circuit can be isolated and some other circuit can be switched in, right, that kind of thing can happen. Like for example, in a memory design, if you have a memory, when a memory test is written, there is a possibility, it is like now you have some terabyte memory, right? So while doing test, if say one sector of a memory and a few megabytes of the memory is faulty, you don't throw away the entire memory chip, right? So it will be such a wasteful use of the resources available to us. So there could be there will be an provision to isolate that particular sector of the memory, few megabytes of the memory which is not enough when you are doing the March test. Okay, and the result is failing. So that set of memory probably can be isolated, and you can use the rest of the memory. right? So that can be done. If it is fully faulty, then you might want to pop up a warning that okay, that needs to be replaced or things like that. And then you can go to the board. At the board level, you could see okay, this chip whether it's working or not, or you could tell the user okay, this particular chip isn't working, so you need to replace it. And at the system level, this entire board also can be replaced, right? Most of these boards these days, they come in as an plug-in version, right? Chips are generally, you can't replace one particular chip, but the boards are definitely replaceable. So the entire board, if there is a fault with the chip also, earlier days when you had that chips on an socket thing, you could remove, but these days it is an SMD soldering, and most of the chips are can't be removed from the board. So the board itself needs to be discarded in case there is a problem with the chip. So this is the now how do we implement this, right? So there will be a test control. Now this test control, obviously in the test control there is an in the RAM some program will be written, and all the test data will be stored in the ROM. And that will come to the test controller, and finally you need to generate hardware signals, right? Test patterns. So this test patterns is zeros and ones, the signals, right? Physical signals needs to be generated to circuit to do the testing of the circuit. So there has to be a hardware pattern generator. Now during the normal mode, this is isolated and the primary inputs is given. So you need to have a multiplexer. So that will be controlled. So everything is within the chip here. Right, so you have an input mux, and you have a test controller, you have a hardware pattern generator, and while testing, the pattern generator output will be given to the circuit under test, and during normal operation the primary inputs will be given. Right, and then you have the primary outputs for normal function. In case of test, okay, it will go to a response. Okay, now each and every for every test generate input which is given, we are not going to check whether it is correct or not with respect to the data available in the ROM. So what we do is we compress the entire results, okay, into one particular data, and then we compare. Okay, so if you are running 1,000 tests, 1,000 results will be compacted into say one result. Okay, that aspect we will see. It is known as signature. Okay, that it is known as a compactor. That means the entire results will be compact, and you have a single result coming out of 1,000, and then it will generate one 64-bit data signature or something like that, which we'll compare. And if it is not matching, then we might again rerun a detailed analysis of each input. Okay, so but in the first go, we will use a signature, so that will save the total time. Okay, because you don't expect things to fail very often, right? So it is failure is an exemption than an usual occurring. Okay, so that is the reason we use a compactor. So there are several ways of generating the test pattern. Okay, first is the ROM. Okay, in the ROM you could like we did, right? For every circuits we found out what are the total. We can write 10 ATGP program and find out what are the test vectors, and all those test vectors from the ATPG can be stored into an ROM. Okay, so this is very expensive because all this entire test vectors to be it might run into thousands, and putting it into a ROM and then picking up one each is not a good solution, because we have better solutions. Okay, and one of the things which is used most widely is known as the linear feedback shift register. Okay, this uses very little hardware and is the currently preferred BIST pattern generation. Okay, it generates random test pattern. Okay, not in a sequential manner, and it may not cover the 100% of the test vectors. Okay, it will randomly generate test patterns which are given to the test vectors. Okay, so we will study about this in the subsequent slides. Okay, or within the chip you could have a binary counter. Right, binary counter is for exhaustive testing. So you could have an binary tester which will count from 0, 1, 2, 3, 4. It will keep running like that. So those test vectors can be given to your test system. Okay. Now again, for example, for a 64 bit system, okay, at 100 megahertz clock, it will take these many hours to generate all the test patterns. Okay, so this is again not a very good system. Right. What happens with a random test pattern is one test vector can probably cover so many faults in one go. Right, that we saw that one test vector can cater for several faults in a system, right? And hence, as you keep increasing the random test pattern, almost 80 to 90% of the faults will get covered very soon, and then you can stop the these, as it's increasing binary now, so we are not considering that each test vector is being checked multiple times, right? And there will be many test vectors which are just repeating the same results, or it is not generating any results. So all those things, it is just a pure simple binary counter which will keep doing. Okay, so this is it can do an exhaustive testing, but then it is not preferred. Or you could modify the testers also. So but if you know very well the test pattern, counters can be designed, right, whichever way you want to count, right? So you all have learnt sequential design, where you could have a modulo 3 counter. It is only counting only 3 and going back to 0, or you could have a gray counter, right? Any counter for that matter, any sequence. So this is a modified counters you could have, but this is the one which is again the one which is most widely used. Okay, you have an LFSR in which you cover most of the, say, 80 to 90% of the thing gets covered, and a few will remain because this doesn't give 100% coverage. So what is remaining, those test vectors can be put into the ROM. Okay, so it is an mix and match of the first two. 80 to 90% gets covered here. The remaining 10%, which is not getting covered by the random test pattern generation, will be covered by the ROM circuit. Okay, so this is a mix and match of that. And then you could have cellular automation, and that means for you divide the entire chip into small cells, and you could have an small pattern generation for each of those small cells. Okay, so rather than within the chip, rather than having a centralized LFSR, you could have small pattern generators within the cell. Okay, so that is another approach. Okay, but the fourth one, the second one and the fifth one are the one which are mostly used. Okay, we'll see our random test pattern generation, it covers 80 to 90, but if it is for a critical application and you would want to do 100% fault coverage, okay, then you could go for LFSR and ROM, right? So but if your yield is very high, you know that, then obviously if the yield is high, you can relax your testing pattern, right? So in that case you could restrict to LFSR. So, let's talk first a little bit about exhaustive pattern generation. If I have a circuit like this, okay, I have 1, 2, 3, 4, 5, 6, 7, 8. Can you tell me what is the total number of test vectors required? Is it 2 to the power of 8 and 256? We have learned so many techniques of testing till now. We are coming to an end of this course. So just having a look at this particular circuit, can you guess whether it will be 256 test vectors are required?
No, sir.
Yeah. Then how much is required? There are 8 different
Around
for
20.
exhaustive checking. For exhaustive checking, there are 8 inputs. Anybody? Yeah, Jay, Ranjani, anybody can make a wild guess how many test vectors will be required?
Sir, around 30, 40, considering like test sites.
No, you can see that these cones. Just have a look at this cone, and can you make a guess?
64, sir. 64 plus.
Yeah.
2 to the power 5. 2 to the power 5 plus 2 to the power 5.
Yes, 64 exactly. Right. Because if you see here, this test vector 6 has nothing to do with this cone. Right, 6, 7, 8. So we can, when we have circuits like this, more often than not, circuits are like this, practical circuits. So we can have 1, 2, 3, 4, 5. Right, these 5 test vectors which will do the analysis of this particular circuits. So 2 to the power of 5, 32 test vectors will be required there, and you have 4, 5, 6, 7, 8, and which will do an analysis of the bottom portion. Okay, so total 64 test vectors are good enough to test this particular circuit, and not 256. Okay, so this is what is required. So what we have is, we can have an exhaustive testing. Okay, so you have a 5-bit counter here. I have an 5-bit counter here. So initially I give there is a mux. Okay, because these two test vectors 4 and 5 are common for both the circuits. So I give a 0 here. So 1, 2, 3, 4, 5. So these 2 bits from this counter is available here. So 35 test vectors will be generated, and you monitor the output at H, and then I put this now a mux in control signal as 1. Then these 2 lines will be routed to X and 5, and then I again run 32 test vectors. Okay, so that within 64 test vectors, this particular circuit has to be okay. And see, most of these things, right, the automated thing doesn't work here, right, and it's the human intelligence, and that is the reason in the test engineers are paid heavily these days, and they are the ones most important in an VLSI industry. Okay, the ones who who are more dedicated are put in as are employed as test vectors, because here a little bit of creativity and innovative thinking is required, and the machines themselves, they don't come up with these kind of solutions, automatic test pattern generators and things like that. So if you have a knowledge about the circuit being designed properly, so this itself is an you can call it as an art where to minimize the testing time. Okay, art and science, you could, right, where human beings produce better results than machine. Right, there are other ways of doing exhaustive pattern generation, which is known as a hardware partitioning. Okay, this is like if within the chip you cut the circuit into smaller sub circuits, and each of those sub circuits become controllable and observable. Okay, so you can do an exhaustive testing, right? So instead of a big circuit, you will have so many variables and so many tests. So once you make it into small circuits, okay, this is kind of making a cut, right? Something similar you could do here. And the other one is again, it is also a kind of partitioning, sensitized path segmentation, but based on the signal flow path. Okay, so Okay, you could divide the circuit like this, okay, because the signal is moving like this, okay, across a circuit. So this is one path. So you could, there could be n inputs. A is not an, there could be right n inputs, a set of inputs going into this block, a set of inputs going to this block. But you can, as per the path, you could do the testing, okay, and then you could have some partial hardware. This is a combination of these two again. So these kind of things can be done for exhaustive pattern generation, right? Then we have something known as pseudo-exhaustive pattern generation. Okay, for this particular test vector, there are two mugs now to be tested. Okay, so there are 4 inputs here, 4 inputs here at control signals. So total test vectors required, right, for each you could call 2 to the power of 6, 64 test vectors will be required to check this multiplexer. 4 inputs, 2 control signal. So for 0 0, this 0 will be routed. For 0 1, again for 0 0, either a 0 can be transmitted or there can be 1 which can be transmitted, right? Similarly, for 0 1, okay, from here a 0 can be transmitted and 1 can be transmitted. So if you just blindly tell the system ATGP to do it, it will, what it will do is 1 2 3 4 5 6. So 2 to the power of 6 test, it would generate so many combinations. Similarly here also. Now if you see here, now for these two together, we can have just 8 test vectors, which will more or less give the functioning, will tell us that this would function without any fault. Okay, so now the first test vector is given as 0 0. Okay, for both these chips. Okay, 0 0 and I am giving 0 0 here. Now all the inputs are given 0 here. Okay, these are zeros and these are also zeros. So at the output I will monitor 0. Okay, then I will change these for both these chips. I will change 0 to 1, 1 to 0 and 1 to 1, and I will monitor these outputs. Okay, zeros. Okay, so what does that give me? What this tests, what does it confirm? What functionality does it confirm?
There is no staccato on the fault.
Yes,
Anyway.
yes, you can say all the zeros. Okay, the function is all the zeros are getting transmitted, okay, properly. Okay, so it tells. Then again, what I do is I put a 0 0 here, right? I give 1 only to the 1 input, right, here. And check the output here whether I am getting 1. Others are zeros. Okay, here. So if others are zeros, I can also confirm that this 1 is not getting shorted internally. This 1 is coming out here, and within the mux, okay, this 1 is not getting shorted to ground. So this so that is the reason I am putting zeros here. Okay, and I am still getting a 1 output. Okay, so it indicates that this 1, when I am giving 1 here, I am getting 1 here, I am getting 0 here. So this 1 is not internally getting shorted. Okay, so I get a 1 output here. So similarly, I put 1 in the next. I put a 1 here and I give zeros everywhere, and I give the control signal to route this 1 here. So this is right. So this is no way it is an exhaustive testing, right? It is just one. It saves a lot of time with just 8 vectors, but you could say 80 to 50 to 80% this chip would function without any faults. Okay, because functionally it is okay. Okay, so this is again one kind of pattern test. Obviously a machine cannot think of these kind of solutions. It is the human element which can come up such solutions for these kind of problems. You could have a slightly better solution out here, slightly more exhaustive, right? It is again a 20 vector testing, okay, for this particular example. I give 0 0 and all zeros out here. I am getting an output 0. Again I am giving 0 0 and I am giving an 1, right? Others are 0, okay, so I am getting at both the places 1, okay. This is also, then I am giving 0 0 and I am giving a 0 here. I am giving a 1 in the adjacent signal. I am giving 1 here and I am giving a 0 here, and I am trying to route this out here and just verifying this one whether it is going to get affect my output, okay. So that is again 0 0. I am giving a 1 at the third pin, and I am getting a 0 here. That is fine. I am giving a 0 0 and I am giving a 1 here. So this is slightly more exhaustive than the previous one, okay. Then again I change this 1 0 1. Initially I transmit a 0, okay. I am getting an 0 here. Then I am putting a 1 here and I am still confirming whether I am getting an 0 here. Then I am giving a 1 here, okay. In this case 1 needs to come here, and then I am right, and I am giving 1 in the adjacent cell, adjacent input, and I should get a 0. So this is a 20 vector testing. So all these things can be done, right? So these things, if you can think of how to ascertain the functionality with a minimum number of test vectors, but you can think of more test vectors. Again, it will increase the time, but for a mux, okay, these two 8 vector testing and 20 vector testing is generally considered as a very good test vectors to identify any fault. Okay, so with great confidence after this test and with these 20 test vectors, you could say this would work. Okay, so you don't have to do an 100% exhaustive testing. Okay. Now we take up the one which is mostly used in the chips, which is known as random test pattern. Okay, so what we do is we take up some a random pattern generation. It will generate patterns in a random manner. Okay, a random manner means it is not sequential. Okay, it will keep pushing some data in a random pattern. And generally in the initial you will find these are the fault coverage. Okay, so it will, so if you generate large number of random patterns, okay, obviously most of the faults will get covered, but generally around 90 see if you see here, okay, if you run 100 test random patterns, more than 95% of that is getting covered here, right? So from 100 to 1000 it is again 10 times, right? So you might want to stop at 100 and cover, okay, almost 95%, and then from here to here in the ROM, for if you want, okay, you can either leave this, okay, because generally when we are doing an test, when we are doing testing, we saw in the very first class DPM, a figure of DPM, right? In that we said if the yield is very high, then your fault coverage can be low, right? Because you are very sure that your yield is very good. So in this case, if your yield is very good, you could leave at this 100 itself. But if their yield is bad, that means you are not very confident of the way it is being fabricated, and you want to do on a good fault coverage. In that case, these test vectors can be put into an ROM. Okay, so that is the one. Now we'll have a look at what are the ways we can generate these test vectors. Okay, so this is known as linear feedback shift register. Okay, now you see, I suppose I have somehow initially I need to initialize this. Okay, otherwise this would not function. So I should have an a way to initialize these registers. Okay, so if it is in 0 0 0, okay, it will get stuck at 0 0 0. So when the test cycle begins, I should have a reset or a set for each of these flip flops. So suppose I put in 1 0 0 initially. Okay, so that is important that for all these linear shift back registers, you should have a provision to push in the initial data. So 1 0 0. So if you see here, here, so this 1 comes here, so this 1 comes here, this 0 comes here, so this 0 comes here, and here it is an exclusive OR of this and this, right? So so I have an 0 being pushed here because this is an exclusive OR. So exclusive OR of from here, right? So I have a 0 being pushed here. In the next stage, this 1 comes here and this 0 comes here. Now I have 1 and 0 here, right? So 1 and 0 exclusive OR will be 1. So then 1 will be pushed here. So now similarly when the test runs, so this is the pattern which gets generated here. So this is what 1 0 0, right? This is an 4 and this is 2, this is 5. So you see it is not in a sequential manner, and also you will find that 0 0 0 is not there, right? So not all possible combinations are generated. Okay, so it is possible that it depends on the design whether all 8 are possible, only 7 is there, only 6 is there. Here in this cases 1 2 3 4 5 6 7. Okay, 7 unique patterns is generated. It could be only 3 unique pattern, 4 unique pattern, 5 unique pattern. The way these have been interconnected, it depends on that. So you could have the length of this pattern could be anything. Obviously, maximum for this 3-bit register, maximum test pattern can be 8. Okay, that also could be possible. It might be reading from 0 to full. Like for example, a gray counter, it can do anything, but in a different, not a sequential manner. So that kind of test pattern generation is possible out here. Okay, so this is what is known as the pattern linear feedback shift register. So these patterns can be generated out here. Now this is another circuit. So if you have you can have an n number of flip flops connected, and they can be connected like this. Okay, so there could be different pattern methods of connecting these gates. Okay, here XOR gates. Okay, this is done like this. You could also have, right, different patterns, not necessarily this pattern. So each of those patterns will generate. You could have inverters in between out here, or instead of these two, you could put an AND gate out here and doing it like this, right? So all of them will generate a different set of patterns. Also, not only that, say one for one particular circuit, okay, I require a set of patterns. For a different circuit, okay, I require a different set of patterns. Okay, now say this is a 32-bit chain, so it can generate say for example, say 1000 patterns. Okay, now if that I can generate a different set of 1000 patterns by initializing this with some other pattern. Okay, right? So suppose I give 0 0 1 0 some initial load. If I do, it will generate one set of pattern, but instead of this value, if I put some other pattern there, it will generate some other series. Okay, so this one particular circuit can be used to generate different kind of test patterns for different circuits. Okay, right? So that whereas, and that is what generally we'll have one probably when we saw here, here this is here it takes care different LSRs for different small neighboring gates, but in this we have one LSR central LFSR generating various test patterns for various circuits. Okay, so it is not that you have one LFSR which will generate some random pattern which will be applied to every circuit. Okay, that is not the case, right? You can customize this particular circuit, okay, by feeding the initial data accordingly and generate the kind of set patterns. And also from the test controller, maybe this XOR gate, you would want to use an mux out here and isolate this and put it directly 0 here, right? That kind of thing is also possible to generate the required test pattern, right? So it is not that one universal test pattern will be applied to every circuit. So depending on circuit to circuit, this is one a block, and the pattern can be controlled, okay, by two things. First, by changing the initial data, okay, by the set reset pins, asynchronous set reset pin, input data available for this flip flop. Second, by modifying this feedback network here, right? You could have muxes in between, which could change the way the feedback is given. So if you change that, the feedback also changes. Okay, so is this thing okay with all of you? Is it understood? Yeah, Jai Singh, Gokhale, is it okay?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay.
Yes.
So so this is again the same thing. It says initialization is very important. Okay, it says with each initialization. In fact, what is done is like in you have your WhatsApp and things like that, right? Where the data is end to end and encrypted, right? What it does is you will have some random pattern generation like this. Okay, and you have your data. Actual data, you put an XOR with this, okay, with this random pattern. So what you get here is garbage, okay, you can't make sense out of this. At the receiving end, you have another XOR gate, and you have the same pattern generator there, okay, and this pattern generation and this pattern generation, they will be in sync, okay. Again, you do one more XOR and you retrieve back your data. Okay, so so this initialization of this, okay, this data, okay, that particular this, although the hardware will be same for every mobile user, okay, but the pattern, when I am speaking to Jay, then this my data which will be fed here for generation of encryption will be different. Okay, and it will be known only to JS mobile. So only me, when I establish a connection, okay, my mobile and his mobile will get initiated with the same initial values in these registers, and they will generate the same pattern. For a third party, if he is intercepting, he will not know, right, because this is a 64-bit long register, suppose. So from the 2 to the power of 64 different combinations are possible. So unless he knows what was initialized here and what was initialized there, they cannot decrypt the data. So that is used in cipher also, okay, for security also, these kind of things. Okay. So when we have this, when we are applying the test vectors, okay, let me go back to this slide and explain. Right, now this output response is coming, right? So you are applying, say, 1000 test vectors out here. Say you are applying, say, 1000 test vectors here, okay, to this from the random test pattern. You have 1000 responses coming here. Okay, now what to do with that? Right, so one is with those each of this, say it is a 64-bit output, right, suppose like this, some 64-bit data is there, right? Now I can have that 64-bit correct result in my RAM, and I compare this with that RAM, okay, and then say, okay, this test is pass or fail. Okay, now it will take that much more time for this to do that, right? If you start comparing. So for that, what we can do is we can do something known as compactization to save the total time which is taken to analyze this result. Okay, so what I can probably do is I can say check whether the parity here. Parity means whether it is a total number of ones is here, if it is even or it is odd, right? And in the actual fault-free condition, what will be the parity, right? So I can just check that parity and keep moving forward. Okay, so that will be much faster than comparing every bit by bit, right? Or I could I can just check the total number of ones which are required, right? So once this data comes, okay, this will be mapped as an even parity or an odd parity, right? And from here also it is even parity. So this will speed up the total test time. Okay, so this is known as compactization, where you are not checking actually bit by bit, okay, with the fault free information which is available in the ROM. But overall, if you see, so the possibility of two errors like is very minimal, correct? So as such, the faults are going to be the possible probability of fault is going to be very low, because you are making a circuit your fabrication, you have taken all care that it will be fabricated free of fault. But one odd fault can happen, but the possibility of two faults will be very minimal. Okay, and hence even in a parity check or the number of ones which are counted, that will be good enough. Okay, so that is known as compactization. The other thing is compression, right? All the test vectors, you can run a full test vector, and the entire data will be compressed and saved, like you have a zip folder and things like that, right? So that later on, once if there is some mismatch, you can recall that particular data and do a further analysis. But this will require more memory space, so these things are not done at all. And even this is not done these days. Okay, compactization also takes a lot of time. So what is done in today's VLSI chips is something known as signature. Okay, so this is very it will finish off the fast the analysis in as the test vector is being applied, new test vectors. This data will keep generating signature, and end of the entire test run, the signature will be mapped with the signature which is generated from a fault free circuit. And only if there is a fault, okay, then you run only one set of test vectors to further diagnose it. Initially, the entire test vector is the entire set of test vectors is run, and you get a single signature. Okay, and if that signature is not matching with the desired with the signature obtained from a fault free circuit, only then we then dissect this entire test vectors into small sets, and then we do a subset and try to find out where the fault is. Okay, now what is this signature? The signature is only combining the test many hundreds of test vectors into one particular 64-bit or a 24-bit. Suppose I have so many data. This is for a single bit. Okay, there are 100 bits which are coming here. Okay, now what I am doing is I am delaying it that stream and putting an XOR and putting it into a counter. Okay, so now if the pattern is say 0 0 0 0 coming in, okay, so so one delay here, it won't make any change here. So whenever there is a 0 and followed by a 1, okay, so there will be a 0 here, there will be 1 here, so it will generate a 1 here, so it will enable the counter. Okay, so so this is a counter enabling signal. Okay, so if it is a 1, okay, the clock will be gated through this. So or you right. So whenever there is a 1, the clock will be set and the counter will make an incremented. So this is, the clock is gated with this signal. Okay. Similarly, if it is a 0 and a 1, or a 1 as a 0, so whenever there is a transition in data, this will be enabled. So this counter will keep counting the total transitions in the input data. So you have an 100 bits coming. Okay, from a fault-free circuit, I will run this algorithm, and I will know for a fault-free circuit, this is the counter. Okay, this counter should reach, say, for a 1000-bit data, for example, say 250 should be the count. And when I am running the test again on a circuit under test, if I am getting 250, then there is an I can say, okay, there is no fault. Right, and if it is more than 250 or less than 250, I can assume that there is some fault. Okay, again, the assumption out here is, okay, there is only one fault. Okay, so the possibility of, so there could be two faults, and which could again result in this figure, right? But then the possibility of two faults is very, very negligible. Okay, so all these test patterns, in fact, in the many of the 8TGB generation things also, we assume that there is only one fault. Okay, multiple faults are generally not considered in VLSI circuits. Okay. So now you have this, right? This is an example of this pattern being given. Okay, 0 1 1 0 1 0 out here. Right, there is an if there is a stuck-at fault out here. Okay, this is the pattern which you get. Okay, this is the pattern which you get, right, which is shown here. Now, if there is no fault, I think if there is no fault, this is the pattern, right? You have an 0 here, 1 here. Okay, so this is not an AND, so I'll get an 1 here. Similarly, right? So for all these patterns, so you will find this is the pattern. If it is not a fault, and this is the pattern. If you have a fault, this is the pattern you will get at this node. This pattern, right? If you see here, the total number of transitions. Okay, if you give it if you give it to this circuit, okay, this pattern is given here, right? So here I have 1 to 0. And 0 to 1 and 1 to 0, it has 3 transitions. Okay, now with a fault out here, okay, I am not very sure whether this is with fault or without fault. Okay, that you can analyze, but there are two different patterns will be generated, with and without the fault. Okay, now here if you see, there is only one transition, so the counter will be only 1. Okay, so for this particular fault, for these kind of test vectors which are coming in here, and if I feed this output here into this particular single bit signature register, this is known as these two circuits along with the counter is known as the single bit signature register. Okay, so this will generate a count of for a fault free for this particular test vector, for a fault and fault free, it will be 1 and 3. Okay, it will be different, so the number of counts. So with this you can make out where there is a fault or not. Is this scheme okay with all of you? Is it understood? Yeah, Jai Singh, is it okay?
Yes, sir. Yes, sir.
Okay. So now this is talking about a single bit, but you could have an 8-bit information coming, right? Parallelly from several outputs. Like here there are 2 outputs, right? So there could be several outputs. So many of them can also be combined into a multiple input signature register. Okay, so this is 1 input, 2nd input, 3rd input, and a 4th input. Okay, this will keep combining the data. Okay, like this. Okay, so all these connections need not be the way it is shown here out here, right? Here this and this is done. So you could have this input coming from here also, right? Or it could come from this stage also. Okay, so it's left up to the test engineer to decide what kind of signature he wants. Okay, so depending on that, it can basically mix up all the informations of many test vectors. That could be run into lags also, right? So in certain VLSI circuits, now if you have 64 different pins and you want to do an exhaustive checking, okay, this can mix up all those outputs into one and then check for the signature. And if the signature fails, then you can again do small test. Okay, so you can call that subroutine later on. Okay, so in the first go, assuming that there won't be any fault, you could just do an overall system check using this. Okay, so this is known as multiple input signature register, right? And then we have something known as a BILBO, that is a built-in block observer. Okay, yeah, it is written here, built-in logic block observer. Okay, so this is the thing. This can do.
Sir, that single bit and multi-bit, it is only for combinational circuits.
No.
Or it can be.
It can be. It is like you have a circuit under test. You are giving some test patterns. Okay, so you have certain outputs coming, right? If these test patterns are okay, right? For a sequential circuit, again this pattern followed by that, right? 0 followed by 1, right? It can have, right? So this will combine that series also, right? So this can cater for the sequence. Obviously, delay it won't. Delay also, you could say it will check the delay also. Okay. For example, if you are running it at the rated clock, right, and because of delay, okay, because of some excessive delay, this data has got corrupted. This is, instead of capturing a 0, it has got captured 1. Still, the signature would change, right?
Yes, sir.
Right. So and then since it is an continuously data is being not only one data, a sequence of data is being captured here for the signature. Even the sequential logic thing also will get captured. So you can say delay also, but for a delay probably you would want to run it at the rated clock, okay, and see whether these data are being captured. So all the tests what is being done is will for delay, bridging faults, all the faults can be captured here, right?
Okay.
So this is known as a built-in logic block observer. It can do this is depending on the control signals. These are the two control signals, B1 and B2. Depending on the control signals, this can be configured, okay, as a normal flip-flop or as a linear shift register, okay, or as a compactor, okay, or as a scan. So there are two inputs, okay. So depending on whether it is 0 0 0 1 1 0 or 1 1, okay, the role of these flip-flops they can change the way they function, and they can do one of these functions. Okay, so that is explained in the subsequent slides. Okay, now here it says 0 0. Okay, 0 0 means what happens if I put a 0 here. I think all these AND gates will not function, right? 0. Another 0 is coming here to the mux. Okay. So if it is mux, then I have this serial data coming into the mux. Okay, this D1, D2, D3 is coming from the combinational block. Okay, this is coming from the combinational blocks. Okay, the circuit under test. Okay, so this is, so now since this input is 0, this serial in data will be put into this mux, and from here that data would come here. Right, and I think I will have an since it's an mux, this is 0. I think it will be a 1 here, right? Okay,
it should be 1, sir.
Okay, this will be a 1 out here, and here also there will be a 1. So the serial data here will be available as a serial bar out here, and since this is 1 here and this is an XOR gate, again I will get the serial data out here. Okay, that means whatever input is given here, that gets loaded into this D flip-flop, and this output of this D flip-flop will come here, and this output of this D flip-flop will come here. So when I give B1 is equal to 0, B2 is equal to 0, whatever serial data is given here, okay, I'll put 0 0, and in all the flip-flops I will put the test vector which is required for giving a test. Okay, so this pattern can be generated by the random test pattern generator, right? So once that pattern is available, if it's a pipeline structure, what I'm going to do is I am going to put that pattern into this, okay, into all these registers. So it will put it onto all the registers so that the necessary test vector is available here. So the first thing will be to put this into 0 0 and then scan in the data and put it into all these registers. Okay, so this is the first mode. Okay, so is the first mode clear to all of you? Scan.
Yes, sir.
Okay. In the okay, this is the scan mode. Okay, so this is shown in a bold. Okay, how the data would flow. This is what we just discussed. The second mode is where it is 0 and 1. So it says it will act like an LFSR, okay, a pattern generator. Okay, now how does that happen? This is 0, right? And if it is 0, I think this will be 1 here. Okay, all these will be 1. And this output is available here, right? And here also it will be 1. So this data, inverted data, will be available out here, right? And here it is 1. Okay, here B2 is 1 out here. So instead of this serial data, it will not take the serial data, it will take this data, and this is coming from the feedback circuit. Okay, so now all these flip-flops will be connected like this, right? So because there is a mux out here, so this data, okay, from all this XOR data, that is coming here. Okay, so so this data is being picked up here. Now it will generate the pattern generator. So is this okay? How this pattern is getting generated? Right, I have for 0 1, right? So 0 1 is going to put 1 here, so this is going to invert. Okay, and then instead of the serial data, it is taking data from the this feedback. So this particular circuit out here will have a set of XORs like we saw here, right? All these XORs. Okay, so all those XORs are placed in here. Okay, so that is the mode of operation, right? And in the third mode, it's a normal flip-flop mode. I give 1 and 0. So I give here a 1, right? So now if I give 1 out here, this will be enabled. I have a data bar coming here, right? At all these things, it will be a D1 bar here, and I will have a D2 bar here. I'll have dn-1 bar here. So because this is a NAND gate, I'm giving 1 here. So this NAND gate will become transparent, but because of this bubble, this input will get inverted. And now I'm putting an B2 is 0 here, right? And in that particular case, what is coming out here is since B1 is 0, I have this as 1 here. Okay, I have this 1 here. So even the mux is being activated from 0, but it doesn't make any difference, right? Because I am giving B1 as 1 here.
Sir,
So
B1
will be 0 here.
So B1, yes,
Yeah, it will be
sir.
0 here. So it will be 0 here. So it will be 1 here. So this is isolated. Although this mux is activated for serial in, this is isolated. I get a 1 here. and this is an XOR gate, and if I give a 1 here, this D bar comes as a D here, right? So it works like a normal, like you have a combinational block here, okay, and the data of the combinational block is being captured by this, okay. So during normal function, this can give, or while doing testing, first I can scan in the data and then switch it on for 1 clock cycle to the normal mode. So depending on the test vector, now whatever the combinational logic has synthesized the test input vector and gives the output, that can be captured into these flip-flops by setting this 1 0 for 1 clock cycle. For normal operation, it will continuously remain in 1 0, but during testing, first we put the serial in data complete for all the flip-flops, then for 1 clock cycle we will make it as 1 0, right? So that can be done, and then finally I can use it as a 1 1, right? If I use it as an 1 1, if you see here, then it will work like I have this 1 coming here. So this data which is coming here, this data which is coming here, right? That will come here and it will work like an compactor, right? MISR. It will transform this into where this is the compact signature register, right? So this will become okay. These XOR gates, okay, these XOR gates are the ones which is placed below, right? Now this will work like an compactor. So these XOR gates, okay, these XOR gates are the ones which we are talking here, okay. So that is the reason these XOR gates have been placed here. So in 1 1 operation, these XOR gates, okay, they are going to come. So it is shown in the MISR board. So these XOR gates will come, and continuously the data will come here, and it will generate the signature. Okay, so you can just give this 1 1, and you keep running the test waveform. So this is one universal register. Okay, so you could have these universal registers, and depending on the control signals, you could program this for the one of the 4 operations. Okay, so now so I hope this understood. You have understood the 4 modes of operation of this, right? So all these things are there is whatever today we discussed today, right? It is nothing to do with your number of pins or from the external test bench. All those, it is being generated internally. The result is being analyzed internally, right? And finally, if the signature analysis fails, only then an outside interference is required. Otherwise, you power on the switch. Okay, initially itself in the ROM there will be it will get it when built-in test mode, and it will run the built-in test, and then only it will go for the normal operation. Right. That is why many a times in our PCs and all, when we switch on. Right, and it will take some time for everything to get booted and then make it usable for us, right? Because initially the system is doing a self test. Okay, so it will run the self test, and then it will give that. So for any system, for that means first chip wise, and then PCB wise, and then system wise, it would run a built-in test. So there is no manual intervention required. Test bench and connection to the test bench and all is not required. All this will become part of the circuit. Okay, and now this built-in test, okay, also takes into consideration the scan design. Okay, because we said the scan design makes it, what is the scan? The beauty of the scan design is, you don't, each combinational block in today, everything is in a pipeline structure, right? So every combinational block is connected from a set of flip-flops to a set of flip-flops. So and hence the testing has become very simple, because you are independently able to put data into these flip-flops, capture this data, and unlike in the earlier days, if it is not an pipelined structure, you have combinational blocks which are connected to each other, then it becomes very complex. Now because of all the RISC processors and all, right, they just have small blocks only. They do limited functionality. All the RISC processors, even today, whatever we have, even the big processors are actually RISC processors. From the top level, you could consider that as a complex processor, but there would be a compiler in between which will break those instructions into small RISC instructions, and finally at the hardware level it is a RISC processor. Even most of the modern day processors are pipelined RISC processors. That means the combinational block will be small blocks only, and which can be accessed through this scan design. Right, scan design is only that means it has got flip-flops. You are independently able to access these flip-flops and take data, and combined with that the built-in test. Now built-in test is what it is a scan design only. What we are trying to do is, instead of an external signal through the pins getting into this flip-flop, internally itself within the chip we are generating some random signals and putting into these registers and taking it out, analyzing it. Okay, so essentially it is built-in test is nothing but an scan test only, boundary scan test only. The only thing is, difference is the test is being generated within the chip and the analysis is also done within the chip. Okay, that is the difference. Now coming to like we said in the random test pattern generation. Okay, when we saw this graph out here, right? So if you see here, to have a 90 to 95%, you have certain number of tests, but to achieve 100% from here to here, so you have 10 times the jump out here. So it's very difficult, right? So here, so this is the case in real life also, right? In any organization, right? You have the 20% of the people doing the 80% of the work, right? And rest 20 is being done by the 80% of the people, right? So this graph, similarly, right? If you want to score in your exam 80% marks, you can put 20% of effort and get 80% marks. But if you want to score 100% marks, you have to put for this additional 20%, you might have to put additional 80% effort, right? So this is something similar to that, right? So what is done here is this, although we covered earlier also. So you have a random test pattern generator. Okay, it will generate the test patterns. Okay, but after doing that, and if you want 100% coverage, okay, in that case you can inject a 0 or a 1, right, separately for 100%. So if you want to generate some specific test vectors from the ROM, you could feed in those signals, so that can come here. And then if you see here, this is a NAND gate, and probably if you give a 0 out here, if you give a 1 here, this will become a 0, so you will be able to pump in a 0 out here, or if you give and 0 out here, somewhere out here, then it can generate an 1 here, and this test vector can go here. Similarly, if you have an OR gate, if you put a 1 out here, okay, through this setup, I can force a 1 into this circuit. So this you can do for if you want to do a mix of LFSR, and that means this scheme, right, where we discussed earlier. Here, right? So for this scheme, so this kind of circuitry can be used. Okay. Random test pattern can be used, and After the completion of random test factors, if you want to put a 0 or 1, you could do this, right? And then finally for the memory BIST, right? Again in the memory BIST, okay, generally this is random sequence is not used, okay, because when we saw the march signals, right, you continuously increase the address lines and you because what happens is we in memory, since all these cells are located close to each other, we have to see any change in data of one cell where it is getting affected in the cell which is placed just besides. So you have all this march tests when we discussed about the memory testing in one of the lectures, previous lectures. We so you have a march test. So a random pattern generation is not suitable for memory BIST. Okay, so you generally have a binary counter. Okay, so so we don't use this random pattern generation for memory. And the second thing, if you remember from our memory testing, if suppose this cell is being checked, you select this address, you write a data and you read a data, right? So so writing a data and reading a data, okay, changing this every time it takes more time than doing the address, changing the address cell, and that's why we said once an pattern is done here. So so obviously when we are doing this memory cell, this adjacent cell data is fixed, okay, but what we can do is we can do parallel testing of this memory and a distant memory. That we saw that in our memory testing. So when you are selecting this address, okay, I select this address, do a read operation, write operation. I don't change the data line information. Then I select some memory cell which is slightly far away, do the same test, and again do the same test on a different memory cell. Okay, so that can be done, and then so that kind of testing can be done. It is known as parallel testing, right? Now several kinds of memory test can be done. One is known as the concurrent. Okay. In this, when the system is normally operating, concurrently the memory can be tested, okay, because the whatever is the free memory, you can run a test on it. Okay, non-concurrent means that the normal function will be interrupted and you do a test, but while you do that test, okay, the contents of the memory will get lost. Okay, that is non-concurrent. And there is something known as transparent testing. Okay, it requires an interruption of the normal functioning. Okay, but after the testing, the original memory contents are again preserved. Okay, so these are the three schemes which are available. Okay, so again, this is something known as for memory, right? You have to keep changing the memory address, right? From going from low to high or high to low, correct? And then in that case, you could use this instead of a binary counter. I can use these kind of LFSR. Okay, now this particular LFSR, it can generate 1, 0, 4, 6, 7, right? This pattern. Why is this not going like this? Suppose right, I am testing one memory cell, right? And then at a distant, I am parallel doing. I am increasing the memory and doing a read write operation there, and then I am going here, and then I come back to this adjacent cell. Okay, increasing, right? So it is this cell is not pure binary because I am doing a parallel testing, right? This we saw right in our memory days. Like if I have a memory from 1 to 100, okay, so I do the testing of 1. Right, I do an 5 and then I do 11, I go like that, and then I come back to 2, because the input pattern which is required data pattern for 1, 5, 11 it will be the same. Then I increase go change the data, and then I go to 2, 6, 8. So that kind of memory jump. It is not pure binary, okay, because you are doing parallelly at different locations. So that kind of now you have to go up and you have to go down. So these are the two circuits. If you see, it is the same pattern. It is only in the reverse direction, right? Now 1, 0, 4, 6, 7, 3, 5, 2. Again, you have 2, 5, 3. It is going in the reverse direction. So you can use these kind of LFSR to generate whatever is the memory sequence you require. Okay, so these are the same LFSR, okay, just by the way these are connected. So you could have an mux which is changing these connections, or you could have two independent these things. So these kind of LFSR can generate the required address pattern. Okay, are you all in sync with me? Okay, that for memory test we require to generate address pattern, and although it is march, okay, normally if you are doing a single march, then address will go 1, 0, 1, 2, 3, 4, right? Now if you remember from our memory design classes, okay, I test this cell, okay, there are 5 cells here which I need to test, right? So I'll put some data into all these 4, right? Again, parallelly, because the read write operation takes more time, parallelly I will have a different cell out here. Okay, I will put same data out here, and I will do the operation in this cell and this cell. Okay, and hence this is not sequentially. Okay, jumping from this address to this address. Okay, although it is a march only, but it is a mix and match of doing this march test at different locations, and hence this address pattern will look something like this. Okay, so that can be done by using this LFSR, and and when the output of these memory cells, so like you have a signature, right? So something similar can be used here. It is known as a mutual comparator, because if this is the entire memory cell, you are taking this cell, testing this cell at a different location, you are testing this, but the same input pattern is given at all these cells, right, in the march test, and the same output is expected at all these cells. So you can just when all the outputs are from different cells are available, you can compare if all of them are equal. So the first input comes and you push it through and flip flop here, and the second, and finally when all the outputs are available here, okay, you could compare whether it is same or not. Okay, so you can do that. So this is what address generator from the memory you are getting, and you do a comparator. So you don't even have to have a special ROM for the signature, because for a certain test at different memory locations, okay, all the cells, the information of all the cells is expected to be the same, because you are doing the same march test. Same inputs are given to different cells. Okay, same output is being read from different cells. So they have to be, so you can do an mutual comparator also. That's not a mutual comparator. You can do that. So this is what the entire memory BIST looks like. You have an address and a stepper. Okay, BIST address stepper is nothing but this circuit. It will generate the test signals, and then from the memory you will have a read, and then you have a comparator. Okay, the comparator is nothing but a mutual comparator. So you can do this. So this is a block diagram, a full block diagram of how a memory BIST looks like. Okay, so with this I will stop it here. So